So today we're going to start looking at the final section in this unit in Algebra 2, section 9.4 about this thing called the normal distribution, which is a pretty important topic in statistics. Before we get into our notes though, I do want to give you an example of what this is all going to be about. For example, we're told that the mean height of adult men is 5 feet 10 inches with a standard deviation of 4 inches. And my question for you is, what does this mean? Will there be an equal number of men who are 5'0", 5'1", 5'2", 6'0", 6'1", 6'2"? Would all heights have an equal number of people? What would a bar graph look like? Well, no, the heights are not going to be equal. The majority of men will be close to 5 foot 10 inches. There are a lot fewer people in my region of 5 foot 4 inches tall, a lot fewer people there compared to many of the other heights. The majority of the heights are closer to 5 foot 10 inches. A lot of things in the real world have a distribution like this that we call a normal distribution. For example, we have over here heights of women. Again, most women are closer to the average height of women as opposed to, very tall versus very short. Blood pressure in various patients. The majority of patients have a blood pressure close to the average blood pressure. Fewer people have a very high or a very low blood pressure. Same with SAT scores. The majority of people have SAT scores right in the middle. Fewer people way closer to 800 and fewer people way closer to 200. So we're now going to continue in the notes. We're on page 22 and we're looking at section 9.4 about this thing called the normal distribution. This is going to take us 3 days to get through. So first of all, I have another graph drawn in that shows this normal distribution, also sometimes called a bell curve. And this is what happens when our data is kind of largely bunched up in the middle, like those heights that we just saw, and there's less data on the two ends of things. For any data that forms a normal distribution, we have a couple ideas behind this. I'm going to write 3 bullet points below this graph that we see over here. First of all, the data is what we call bell-shaped, like a bell curve that you've probably heard about, and it is symmetric about the mean. And symmetric about the mean. This is data for an entire population, so my mean is going to be mu. I'm going to mark that at the very center of my graph. The data is what we call bell-shaped and symmetric about the mean. As always, if I'm going too fast, make sure you pause the video to make sure you get all the notes in there. Second idea. Far to the left and far to the right, the curve approaches the horizontal axis, but never touches or crosses it. The curve approaches the horizontal axis, but never touches or crosses it. Which really means that that horizontal axis is a horizontal asymptote. To discuss the specific shape of the curve, we need to talk about 2 terms called concave up and concave down. Concave up means our graph looks like an upright parabola. Concave down means our graph looks like an upside down parabola. And this graph has little bits of both of those. I see kind of like an upright parabola idea here, but then an upside down parabola idea here, then an upright parabola idea over there. We can say that the transition points, where we switch from one of these shapes to the other, the transition points between concave up, which means our graph looks like either this or that, the 2 parts of an upright parabola, and concave down, where we take on a shape like this or that. Maybe I should have used this parentheses. This seems to be confusing this a little bit. We change the shapes at, well, a standard deviation away from our mean at mu plus sigma and mu minus sigma. I'm going to label this tick mark over here as mu plus sigma, and I'm going to label this one as mu minus sigma. And if we look on the graph, that's where I'm changing from concave up to concave down to concave up. I'm going to give you a moment to get those ideas down. Notice that there are more tick marks on that axis. I can label this as if this is, let me see, this is mu plus sigma, so one standard deviation away. This, you know what, I'm not even going to bother. I'm going to just kind of focus on that on the next page. This is all we need for this page, I think. Sorry about that. If you need more time with this, make sure you pause the video. Otherwise, I'm going on to page 23. We have this thing called the empirical rule that will help us understand these normal distributions. I want to zoom out so we can see both the bullet points on the top, and the graph on the bottom. Well, I'm still going to have to move it around a little bit. In a normal distribution with a mean of mu and a standard deviation of sigma, our empirical rule says about 68% of the data lies within one standard deviation of the mean. About 68% of the data lies within one standard deviation of the mean. Or we can say this is between mu plus sigma and mu minus sigma, from one standard deviation above the mean to one standard deviation below the mean. About 68% of the data lies in this region. What I'm saying here, here's my mean. Here's a standard deviation above, here's a standard deviation below. 68% of the data is within that region, actually within those two regions. I think we could probably figure out how much data is right over here and how much data is right over there. We could just divide 68 by 2 and say 34% of our data is from a standard deviation less than the mean to the mean, and 34% of our data is between the mean and a standard deviation above the mean. We're not going to worry about where the 68% comes from. If you take statistics next year, you'll see a little bit more about that. We're just going to use these numbers to do some calculations I'll show you in a moment. Next rule, about 95% of our data over here, I should say, of the data or of our data lies within two standard deviations of the mean. Or another way of talking about that is between mu plus 2 sigma and mu minus 2 sigma. About 95% of the data lies within two standard deviations of the mean. So most of our data is no more than two standard deviations above or two standard deviations below. Well, labeling this over here, that means from there over to there is 95% of our data. I want to figure out exactly what percent is over here and over here. Well, I know they have to be equal, and I know the stuff in the middle is 68. So if you do 95 minus 68, let's do this right now, 95 minus 68, you're going to get 27. 20% of the data is here and here together. If I divide that 27 by 2, I'm going to learn that 13.5% of my data is there, and 13.5% of my data lies over there. Finally, third bullet point. about 99.7% of our data, so really almost all of our data, lies within 3 standard deviations of the mean. So between mu plus 3 sigma and mu minus 3 sigma. So from there to about there, 99.7% of the data, not absolutely everything, because there's still a little more data over here and over there, very small. If the average height of men is 5 foot 10 inches, there's some people who are very, very tall and some people very, very short who'd be in those tails that we're not considering right now. I know if this is 99.7% of the data, though, the amount that's over here and over here has to be 99.7 minus 95, getting 4.7, and you divide that by 2, I'm going to get 2.35% of the data over there and 2.35% of the data over here. And we're going to be using these percents to answer various questions that make use of the normal distribution. Again, this is not quite 100% of the data. This is only 99.7% of the data. There's a little bit more over here and a little bit more over there. These are not numbers you would have to memorize. If we were in class, I would have a poster of this on the board with all these numbers so we can refer to it whenever we need to do our calculations. Let me show you how we can use this. And as usual, if you need a little bit more time, make sure you pause the video before I go on. I'm going to go on to page 24. We're told that adult IQ scores, shouldn't say and, should say are normally distributed with a mean of 100 and a standard deviation of 15. The first thing that I'm asked to do is to draw a normal distribution that represents this data. Well, the very center, I have my mean, and my mean in this case is 100. This tick mark over here is 1 standard deviation more than the mean. I know my standard deviation here is 15, so this is 115. This one will be 130. This one will be 145. Going in the other direction, those are standard deviations below the mean. So 100 minus 15 will give me 85 over there. I'll get, sorry, not that. I'm going to get 70 over here, and I'm going to get 55 over here. Just for fun, I'm going to go and I'm going to fill in some percents that I calculated on the previous page. I know, actually I can't remember these. I'm going to pretend I have this little thing on the whiteboard in front of the class. I'm going to say that's 34% and that's 34%. I know this is 13.5% of my data and 13.5% of the data. And over here, that's 2.35% of the data and 2.35% of the data. In part B, I'm asked to use this empirical rule. The empirical rule is just the rule that gives me all these percents to find the percentage of randomly chosen adults with an IQ between 70 and 115. Well, I care about the region from here over to here. I'm just going to go and I'm going to add up those percents. I do need to see work. It's not a lot of work, though. You just have to show me what numbers you're adding. I'm adding 13.5% to 34% to 34%. Go to your calculator. And I'm getting 81.5% of the data. I can approximate that about 81.5% of all adults have an IQ between 70 and 115. Letter C. I want to use this empirical rule to approximate the percent of adults with an IQ between 85 and 145. Well, 85 is here. 145 is over here, so I'm going to add up these 1, 2, 3, 4 regions. I'm going to say 34% and another 34%, 13.5%, and 2.35%. Again, go to the calculator. and you should be getting about 83.85%, and this is our prediction about the entire population. Out of all adults, we can predict about 83.85% of them have an IQ between 85 and 145. This is how all these problems are going to work. We're going to fill in our tick marks. We're either going to fill in our percents, or maybe we won't necessarily write them in there, but we'll use them from the information that we got on the previous page, and we'll just add up the regions that we care about. Let's look at a few more. Page 25. The blood cholesterol readings for a group of women are normally distributed with a mean of 172 milligrams per deciliter and a standard deviation of 14 milligrams per deciliter. I want to draw this normal distribution. Well, 172 is the mean. Going up by 14, I get 186 and 200 and 214. Going down by 14, I've got 158, 144, 130. I think I might as well go and put in some percents over here. So let's see, from my small little normal distribution over here, I know that's 34, and that's 34, 13.5, and 13.5%, and 2.35%, and another 2.35%. And the first thing I'm asked is what percent of women have readings between 158 and 186? Well, I think you can go do that. Take a moment, figure that out. Just going to add these two sections together, 34 plus 34. We're going to get 68%. About 68% of women will have a cholesterol level between 158 and 186. Part C. Readings less than 158 are considered desirable. So I want to know about what percent of the readings are desirable here. Well, I want things less than 158. So I want this region and I want this region. But I got to be a little bit careful because there's a little bit of data over here. I can't just add 13.5 and 2.35 because that would mean ignoring those people over there. So there's a little trick I can use. I know that all my data less than the mean, less than 172, is 50%. Not from 172 to 130, but from 172 all the way down to, well, whatever. That's 50% of my data. I want to figure out how much data is less than 158. So over here, I think if I do my 50% minus 34, I'm going to get everything that I care about that's below 158. I'm going to do 50 minus 34, and I'm going to realize that 16% of my data is over here. That is not the same value you would have gotten if you added these two sections together, because adding those two sections together is ignoring the very small but significant amount of data that's over here. Two more examples of this. The scores on an exam for entrance to a firefighter program are normally distributed with a mean of 200 and a standard deviation of 20. So I'm going to draw this. Mean is 200, 220, 240, 260, 180, 160, 140. I'll put in some percents. Oh, let's see, 34%, 34%. And I'm going to go get this to get the other numbers from that. I've got 13.5%, 13.5%, 2.35%, and 2.35%. In letter B, I want to know what percent of candidates scored lower than 160. So 160 and everything below, well, again, I'm going to have to do a subtraction idea because I know that 50% of my data is over there. And I know that 50% of my data is over there. Less than 160, I think I want to do my 50%, but take away this region and take away that region. I'm going to get 50 minus 34 minus 13.5. That's going to give me 2.5%. Candidates with scores above 220 are admitted into the program. About what percent of the candidates are accepted into the program? Well, I want to know how many people are above 220. And again, can't just add those two regions because there's a little bit of data over here with the really high scores. I can do this whole region of 50 minus that piece over there. 50 minus 34 is going to give me 16%. Push pause if you need more time here. Then there's one more example we're going to look at. On page 27, a company manufactures engine parts. The diameters of the engine parts are normally distributed with a mean of 3 inches and a standard deviation of 0.02 inches. I'm going to fill things in on my normal distribution of 3, 3.02, 3.04, 3.06, 2.98, 2.96, 2.94. Might as well get those percents in there. Actually, you know what? I'm not going to bother with that on this one. This one's going to work a little different. First, I want to determine an interval for the diameters of the engine parts in which about 68% of all engine parts fall. Well, according to our empirical rule, we said 68% of the engine parts, 34 plus 34, are within one standard deviation of the mean. So I want to basically say any engine whose part has a diameter between 2.98 inches and 3.02 inches would be within 68% of the mean. I'm going to say 2.98 inches to 3.02 inches. 68% is within one standard deviation. Then I want to do the same for about 95% of the engine parts. According to my empirical rule, that means within 2 standard deviations of the mean. Here's my mean. 2 standard deviations this way takes you to 2.96. 2 the other way, 3.04. One more. I want an interval for the diameters of the engine parts in which about 90.7% of all engine parts fall. Well, for my empirical rule, again, that just means within 3 standard deviations. And looking at my graph, that looks like between 2.94 inches and 3.06 inches. So this is our normal distribution. We're going to deal with this a bit more over the next 2 classes, but for the homework, you're going to use this empirical rule stuff to get credit. Make sure, other than problems like this one on page 27, but make sure everywhere else you're showing me the addition problems or subtraction problems if you have to subtract from 50 and things like that. Just numbers by themselves will not get credit for this assignment. Make sure you're showing the addition or subtraction.